So time dilation happens when you go close to the speed of light. So let's look at clocks in a gravitational field. So let's see how time gets affected by a gravitational field. We're keeping it with Newtonian gravity. So this is position A, and this is a height h above the ground. So we can represent its position as a function of time, 1/2 g squared t plus h. And so position A emits a source, emits a light beam, and position B receives it.
Is that now v times t, initial velocity?
There's no initial velocity.
Photon is at rest.
No, I'm saying, so like these are positions of the observers.
Oh, not the photon.
No. So let's draw a space-time diagram for this. Yeah. Okay, so this is A, B. So at this t, A emits a light, and B receives it. We're gonna say this is t1, and then time elapsed before it emits another light, and then B receives it. This is delta TB. So there's 4 events that's happening. The first event, at t equals 0, A emits light. At t equals t1, B receives light. At t equals delta TA, A emits the second light pulse. At t equals delta TB plus T1, B receives second light pulse. Okay, so the distance traveled between the light pulses just should be running short on time. That's good. Okay, so pretty much is the equivalence principle. But we can talk about that later. So right now we're calculating the time difference. How just Newtonian gravity affects time. So right now we are, that'll keep you up. So a pulse gets emitted. So this rocket is accelerating upward at the acceleration of g, accelerating upward. So A emits a pulse and B receives it. A emits a second pulse and B receives it. So we're going to do some calculations when it comes to that. So the distance the first pulse travels is just this distance at time 0 minus the bottom distance at time t1. And that the total distance should just be the speed of light times c1. Because the speed of light travels. So just so people who aren't familiar, so t over x is the velocity. So to get x, we just do the velocity times time. So we get that. And that just equals, so we plug in 0 from here, so just h minus 1/2 g t1 squared equals c t1. Now for the second pulse, the a should just be delta ta minus db. So the time that he receives it is delta tb plus t1, and c t1 plus delta tb minus delta ta. So is this clear? So now we're going to plug in, we're going to substitute the values. So it'll be like h plus 1/2 g delta ta squared plus or minus 1/2 g t1 plus delta tb squared c. Now this marker is not doing me any more justice.
Keep it like this, downward, like temporarily.
Okay, so we're gonna expand this, so t1 plus 2, t1 delta tb squared. Now we're gonna say,
I have a question.
yeah.
So how do they know their time? I mean, they have their watch,
Yes.
So then the T1s, okay, the bulb says, okay, I received the light.
Now we're going to say that the Alice just emits two light beams really close together. So delta T is very small, so we only keep the linear terms of delta TA, delta TB. So this goes to 0, this squared, this goes to 0. We have H minus 1/2 G T1 squared minus G T1 delta TB equals C T1 plus delta TB. Now let's subtract this equation from this equation. So what we get, so these terms cancel out, and this term cancels out, so we just get minus G T1 delta B equals C B minus TA. So bring this over to this side, so I'll C, so divide out by C, bring the TA, so we just get TB equals, or no, TB 1 minus, or minus plus G plus GT1 over C, that's a TA, minus, so the minuses cancel out. Just divide by this factor. And we could use the binomial expansion, which that's just 1 plus x to the n. For small x, which g over t is much smaller than the speed of light, so we just say that's 1 plus nx. Okay, so delta TB is just, and this is minus 1, so 1 minus g, where T1 is just the height over speed of light. So rewrite this 1 minus GHC squared. Okay, and so this is the factor. So the clocks differ between this factor. So the clock ticks faster at a higher point in the gravitational field than at a lower point. That's all that's saying. So that's Newton. So like we're still sticking with Newton. So time ticks differently. And like if you see, like this kind of looks like the Lorentz transformation, v squared over c squared. That's just, something to keep in mind.
How much is this on Earth?
Huh?
How much is this observed?
I mean, to a very small degree.
Don't they say GPS
Yes.
is affected by this?
Yes.
So can you calculate that?
Yeah. So, okay, so GPS not only gets affected by the time, but it gets also affected by the frequency. So all we do is we just invert this statement. And we just reverse this binomial expansion, so we get the frequency of B equals 1 plus FA. And so what happens is, so we could just say GH is just the difference between the potentials. So this is the potential at Alice, this is the potential at Bob. Now we get the frequency to be 1 plus phi A minus phi B, C squared, FA. So now let's just say for a star that, so let's just say at point A, it gets emitted from the star with the gravitational potential of GMR. And then at B, so we measure the frequency of light emitted from the star with this gravitational potential, and then we measure it at a gravitational potential at infinity. So the frequency at infinity is just 1 minus GMR C squared, then the frequency emitted at A. So it gets redshifted. So you could think of it as the photon fighting against gravity. So the photon just fights its way against gravity, and it gets redshifted. So it goes from blue wavelength, which is high frequency, to red wavelength, which is longer wavelength. That's just because the proper time gets increased between the troughs when coming out of the gravitational field. So in order to, so this is all Newtonian, so we could look at gravity, we could just say that the difference, this time dilation, what's up?
So I was just thinking, so GH over C square,
Yeah.
G is about 10 meters
Yeah.
per second square. Height of the GPS is about maybe 100 kilometer or probably 10 kilometers maybe.
Mhm.
So that's 10 raised to 4 and denominator